Hello and again, welcome to the second webinar of our RQ series. Today, lesson 2, we take a look, we focus today on surveying and K-factors of the RQ. Again, Johannes is with us. He is responsible for the trainings in Austria, and he will take care about the training today as well. Again, I do the introduction. So if we go forward, first of all, a little bit of housekeeping. During the webinar, please, all participants, mute your microphones, switch off your cameras. We have planned the duration of the webinar for around about 50 minutes and 10 minutes Q&A. If you have questions, please post them into the chat of the webinar. We will handle all the Q&A and all the questions on the end of the webinar. The Q&A will be moderated by us, and if we are not able to answer all the questions, we will send the questions and the answers by email to everybody. So we are able to cover all questions. Also, the webinar is recorded. At the end of all lectures and all webinars, we will send out a link with all the recordings to all the participants of this webinar, so you can again review the webinars throughout time if you want. So in that case, welcome to lesson 2, cross-section surveys and K-factors. So to say, this is the time for me now to hand over to Johannes, and Johannes will take care about the training. And again, if you have questions, just post them in the chat function and we will answer them on the end. Okay, Johannes, up to you.
Okay, thank you, Christoph. And hello, everybody. Nice to meet you here again today. As Christoph mentioned, I will be going to address different topics of the cross-section survey and about K-factors and some other important topics related to the cross-section survey. So we are just starting with the different types of inputs that we can use with the RQ system and the supplied software with it. So this is a very important part when you start to do the recording of a cross-section of a river or a channel, because you have 3 different methods by measuring the cross-sectional profile of your river. And this is also depicted in the software, in the Q Commander software, and it has 3 different designations. That is height, distance to ground, and sea level. You will see in another training tomorrow where you find these settings and how to select the different types of input methods. So if we start with the height input, this is I would say the easiest method to explain how to record a cross-sectional profile. Here on this illustration, you have a cross-section of a simple channel that is a couple of meters wide and up to 4 meters deep. And you see at the bottom of this channel, with the dotted line here, we say this is our reference level. And from here on, we want to measure the cross-sectional profile. That means the height between the lowest point of the channel and up to different points along the cross-section. Also, we need a reference point in the horizontal direction here. Well, the easiest thing would be on each side or on one side of the river, and I will explain you further on what the properties of a reference point need to be. But for the moment, let us assume we have a reference point down here at the corner, and we say we measure in the cross-sectional profile from this point, from left to right and from bottom upwards. So the first point here would be in an x direction of 0 meters and a y direction of 4 meters. The next point here, or in the profile, would be 2 meters from the reference point on the left and 2 meters from the bottom. And so we continue up all the profile until the last point of the profile, which is about 10 meters from the left and 4 meters from the bottom up here. And also, the water level is measured in the same way. So from the bottom upwards, the water level is in this case 3 meters. And now you will see a slight different version where we can say, okay, we're going to use the sea level as our reference. So the reference point here is not at the lowest point of our profile anymore, but it is depending on the sea level, it is below the riverbed. So in this case, it might be that the reference point or the sea level is 120 meters below the lowest point of our profile. And then the first point here in our profile has the same x direction, but the y direction is different. So if we go back again to the slide before, we have seen the height input is 4 meters, and as soon as we use the sea level as a reference, we have a height, in our case or in our example, of 124 meters. So we add just the sea level to all our measurements of our profile. And again, the sea level is measured the same way. So when we had in our example before a sea level of 3 meters or a water level, we have now a water level of 123 meters. So this is the second option for surveying a cross-sectional profile. The third one is called the distance to ground method. This is probably not so easy to explain, but it is the most common method how you use or how you do a cross-sectional surveying, because the handling is much easier if you do the measurements from distance to ground. Because in most cases you probably have a bridge across the river and you have the channel below it, and you can easily measure the vertical direction from the river edge or the edge of the railings of the river downwards to the riverbed. So in our case, we select a reference point on the bridge. The bridge or the road surface on the bridge would be our vertical reference. And we say, for example, the first point is 2 meters in the horizontal direction and 3 meters in the vertical direction up downwards. The next point would be 4 meters from the edge and 5 meters downwards. And here, please observe, we have positive values measuring downwards. So we do all the recordings as positive numbers from top downwards. This across the whole profile, and also finally for the water level. We do measure the water level, and in this case we measure from the bridge, the road surface to the water surface. In this case, we have a water level of or a distance to the water level of 4 meters. When we look at this profile in the Q Commander software, we can just take the measurements we have taken here. So in the x direction, 2 meters, 4 meters, 6 meters, and so on. And the vertical directions are 3 meters, 5 meters, again 5 meters, and so on. And we transfer those numbers into the profile items of the Q Commander and say point 1 is 2 meters from the reference point in the horizontal direction and 3 meters from top downwards to the first point. So point 1 here would refer to this point, point 2, 4, 5 would refer to this point, and so on. And you can see also here on the right-hand side, you see the scale, the Y scale of our measurements. So 0 point would be at the bridge, and 3 meters would be down here, 4 meters would be down here. And you can see on the left side here that the level measurement is in negative numbers. So here we see that the bottom of our channel would be at minus 7 meters. That is because we have measured the distance to ground from the top downwards. So a level we measured for 7 meters down here, that would correspond to a water level of minus 7 meters. And actually, we don't want to have negative water levels. This is hard to communicate. So we do a trick and we shift our level scale to a 0. So we have a setting in our Q commander that's called 0 point. In the previous slide, we have seen, you don't see it here. We stick to this slide. By default, the 0 point is 0 meters. And in our case, we say the bottom of the channel is our 0. So we say our 0 point offset is 7 meters. And our 0 point is moved from the top downwards to the bottom of the channel. So if we go back again, we see that the scale of the level is shifted from negative values to positive values. And so now we can communicate our water levels as positive numbers, which is the normal case and which is easy to communicate. Just to a brief summary, we have so far talked about the input types that are used in the Q Commander software and which are also used in the surveying of the real cross-sectional profile. And this was height, sea level to ground, and distance to ground. And distance to ground is the most common method to do a cross-sectional survey. So please keep in mind that with this method, we have to add a shift of our 0 point to make water levels positive. And yeah, I have mentioned before that we need a reference point. When we go out into the field and do a river survey, we need to know from which point we do our measurements. Because it can happen that you have to go out again after a flood or after an erosion event, that you have to redo your cross-sectional profile. And so it's very important that you specify a reference point for your cross-sectional profile. And a reference point has certain properties. First of all, you need a reference point that can be used for both the horizontal and the vertical measurements you're doing. This reference point should be fixed. It should never change over years and over decades. So if you come back again, you just go to the reference point again and you measure from there again. It should be very clear or very obvious what the 0 point position is. This can be an edge of a structure, for example, of a bridge, the corner of a bridge railing. It can be a block, like the basement of a bridge. It can be a groove on a bridge structure. It can be an official survey point for geographical surveying or anything else. Then it should be safe from damage. So it should be strong enough. For example, some bridge railings, they might get damaged by an accident. So you have to make sure that your point, your structure you're using as a reference is safe from any damage. And actually the reference point does not need to be right at the river's edge. It can be several meters away from the river, and it is even preferred if that point is much better than a point at the river's edge. So you're better off using the point that is further off of the river's edge than using an unspecified point that's close to the river. And it's very important that you document your reference point. Take some pictures and make some notes and probably get the coordinates from your GPS and document this information. Here you have some examples of a reference point to do your river surveying. So it can be the edge of a river, it can be the end of a handrail, it can be the base of a pillar, or it can be an independent survey point that's never going to change. Yeah. So there are a few things you have to take care of when doing the river survey. One is the viewing direction. So, for example, you go out to this channel here. It's a very simple one, and it can be easily accessed by this road bridge. And you're lucky enough to set a reference point at the edge of the bridge railing. Now the question is, in which direction do you take your profile? So you can actually stay here on this side of the bridge and look downwards, or you can stay on the other side and look upwards. And the question often is, do you take your profile from left to right, or on this side from right to left? And this often leads to some confusion. And a general rule is that you take your cross-sectional profile from left to right when you're looking downstream. So when you're looking, go on the bridge, look into the flow direction of the river, and then on the left side is your reference point, and you record your points on the cross-section profile from left to right. This is also true for the other option. When you're standing on the other side of the bridge and you look upstream, then you have to turn yourself around, look downstream, and again the reference point is on the left side, and you do your measurements of the cross-section profile from left to right. So it's always from left to right, looking downstream. Another thing to consider is you have to keep in mind where you put your sensor and where your sensor looks at. So here in this illustration, we have the sensor here right in the middle of the bridge on the railings of the bridge, and it looks onto the water surface, and the velocity sensor of the RQ sensor produces a measurement spot that looks roughly like this. And depending on the height of the bridge, this point will be smaller or higher. So if the bridge is high up, then this point will walk outwards. And for the profile measurement, you have to make sure that you take your profile roughly on the area where your sensor looks at. So in this case, on this purple area about here. It can be a little bit further up or a little bit further down, but it shouldn't be down here because the sensor just looks on this spot and not on this spot. You can see the same illustration from the side. For example, if we say here on the right side is our bridge, and say our bridge is at a level of 4 meters, and here blue line is water level, then the measurement spot would be 3 meters away from the bridge edge. And say if the bridge is now 8 meters high, then the measurement spot would be closely to 7 meters from the bridge. So you should take your cross-sectional profile around here, where the 7 meters are. On our smaller bridge, you should take it down here at the 3 meter level. Okay, and then if you have done that decision, so you have decided on which direction you want to set your or install your instrument. Is it downstream or is it upstream? So you know how to record your profile. You have all your equipment ready with you, and so you can start to record your profile, to do your measurements from left to right, get the vertical data, get the horizontal measurements, and best way is to record the measurements into an Excel file and save it as a CSV file. And this is most easiest to import it then into QCommander. So as long as you do your cross-sectional surveying, you don't need the QCommander software. You just use a spreadsheet and enter your data in a spreadsheet like shown here, with the position in meters and the distance to ground as well. And after we're finished, we can go into the office again and import those data into the QCommander. Okay, the cross-section profile is one part of our discharge measurements, or the preparation for our discharge measurements, because from the cross-sectional profile we get the cross-sectional area at different water levels. And the other thing is we need to specify the discharge table. So we need to know for which water level we have which cross-sectional area. And for this we need to determine the radar position, the position of the RQ system. We need to know the water levels or the water level lines. I will show you in a minute what that is. And we need to specify the roughness of our riverbed or of our channel bed. So if we look at our profile in the QCommander again, it looks like this. The red line is our profile of our simple channel. And on the left side, in the QCommander, we have our settings of the cross-sectional profile. So we have already imported the data, we have adjusted the level. So at the lowest point of our profile, we have a water level of 0. And at the maximum water level, we have a value of 4 meters. And now we need to specify where our radar is positioned. And here in the settings, we can set the radar position in meters. In our example, we have selected 8.5 meters. And in the illustration on the right, we see the green line at 8.5 meters. This is our radar position. And what the effect is of our radar position, I will show you in a few slides. It can move to the left or to the right. But in general, the radar position is the position where the water is the deepest. There you have the highest velocities. And you usually have the highest velocities at the deepest position. So, and the dotted blue lines here now are the so-called level lines. And these are the lines that are used in the discharge table that is then uploaded to the RQ instrument and which are needed for the discharge calculation. And you can set those lines in the settings on the left side again with this line spacing command. So in our case, we have entered here 0.5 meters. So every half meter, a line is drawn as an input value for our discharge table. And these lines, they should cover ideally the whole water level range you would expect. So in our case, we say we have water levels that can be very close to zero, and we can have water levels that are very close to the maximum depths of the channel. So it can be in some cases that you have a very deep channel, but your water level just goes up a few meters, and then it's enough to draw your level lines just for the lower part of the river. If you don't expect any water level that is further up. And in the commander, you can see at the bottom part of the interface the discharge table, which corresponds to our diagrams above. So we have.
Johannes.
Ja.
Ganz kurz, kannst du bitte die Kontrollbar unter irgendwie ausblenden und das Fenster da rechts weg, da wo du die Session siehst? Genau so, und unter die Kontrollbar sind auch noch weg, die hinter das Bild, haben sie gesehen.
Den habe ich gar nicht da.
Okay.
Ja,
schaust nochmal, vielleicht geht es jetzt weg, weißt du. Okay.
Good. Okay, sorry. When we look at the discharge table, we have different entries here. So we have a level line number. We have a tick mark that tells us is the level line active or not. We have the level, which corresponds to the illustration here. So each level line, so 0, 0.5, 1 meters, 1.5, and so on, is depicted in the discharge table as well. So from bottom upwards, 0 meters, 0.5, 1 meters is our water level. And the Q commander already calculates the cross-sectional area for each of these water levels. Yeah, and that's the essence of the discharge table. Additionally, it has the information about the K factors and the roughness. And this comes in a second, what this means in our discharge table. In general, our Q instrument has a limited storage capacity. So the Q commander only accepts 16 entries of our discharge table. So in our case, we have just 9 entries for our simple profile, like this channel. This is quite enough. But if our cross-sectional profile is larger or is more complex, then we should use 16 water levels for our discharge table. And as mentioned above, we can increase this number by reducing the line spacing here on the left side. So say, for example, we use 0.3 meters instead of 0.5 meters, then we add up additional lines in our cross-section profile. Or alternatively, you can add manual lines to this discharge table. So if you click into the discharge table and click the right mouse button, you can add a manual line and set a level line on your position that you think is important for your profile. And so you can add several manual lines, adjust the water level to your needs, and you can in this way increase your discharge table up to 16 entries. So in this case, for example, when we look at the initial level, initial profile here, where we have 9 water levels, I have added another few lines, and here we come up with 16 water levels, and more at the bottom and less at the top, because we have water levels are more frequently down here than they are at high water levels. So now I have mentioned, or we have seen here in our discharge table, a K factor in percent for each water level. And the K factor is nothing else than the ratio of the mean velocity in the water body to the velocity at the water surface. So it's just a relation of two velocities. And the K factor depends on the shape of the cross-section. So how big it is it a small cross-section, is it a large cross-section? It depends on the water level, of course. It depends on the roughness. Is it a very smooth or very rough surface? And it depends on the radar position. So here we have the formula for the K factor. It's the mean velocity. The mean velocity is somewhere within the water body. We don't know exactly where. And it's divided by the local velocity. The local velocity is on the water surface. And we use the RQ30 to measure this velocity here. And applying this formula, we can estimate the mean velocity within the water body. So, and this relates to the discharge value. So if we say Q, the water discharge, is the mean velocity times the cross-sectional area. And if we introduce the K factor, which is the ratio of the mean velocity to the local velocity, the discharge formula translates to local velocity times the K factor times the cross-sectional area. And in our model, we say our K factors and our cross-sectional profile is defined, and our RQ30 instrument measures the water level and the local velocity. And from these four parameters, we can calculate the discharge of our river or channel. Okay, we have said that the K factor is dependent on the roughness. So you can imagine if we have very large rocks in our river, in a fairly small river, then the flow velocity is lower than in a channel with very smooth walls where there is little friction for the water, and consequently the K factor is much higher there. In the Q Commander software, we can specify the roughness for each entry in our discharge table, and also select the roughness from different methods. So we can select the sand roughness coefficient. We can select the Manning coefficient, which has another scaling here. And we can also select a third one, the Strickler roughness coefficient. You can see here an example of a gravel bed at different water levels. We say a gravel bed has a standard sand roughness coefficient of 100. This is equal to a Manning coefficient of 0.026 and a Strickler coefficient of 38.16. So if we take just the sand coefficient, we see here that the K factor is 71% at a very high water level, and it lowers to 66 at medium water levels, and then increases again to 76 at very low water levels. And the pattern here has to do with the shape of the channel here. So in medium water levels, we have a larger increase in the surface area of the cross-sectional profile than below and upward here. So that explains the shift in the K factors from higher to lower and then higher levels again. But then if we compare this gravel bed here with clean concrete, a very smooth concrete wall, we can see that the K factors generally increase independent on which water level. So at high water levels, it increases from 71 to 77. At medium water levels, from 66 to 73. And at low water levels, from 76 to 85. So this means that we have less friction in a very smooth riverbed than in a very coarse riverbed. And the mean velocity is much closer to the local velocity than when you have a coarse riverbed. We can also see the effect of the K factor, or the effect of the radar position on the K factor. So in the example before, we had the radar position at roughly the correct position in the middle of the channel, where the water depth is the highest, and so in this area we expect the highest flow velocities, and we can also see that the K factor is here in the range of 89 to 100%, depending on the water level. So now if we shift the radar position to the left side and into this slope here, we have a large shift in our K factors, because here at the surface we measure a completely different velocity than we do here where the water is the deepest. And so you can also see that the graph of the K factor to the water level is shifting very strongly depending on the radar position. So the radar position is also a very important point when building the discharge table for the RQ instrument. So then in the second part of my webinar, I will just address some frequently asked topics, how to automate your cross survey or your cross-sectional surveying, and using ADCP measurements and transfer these measurements to our Q Commander software. So often you have an ADCP boat available and you can do a survey across the river. So you put in your ADCP boat here, you tow it across your river, and you get a lot of information, detailed information about the water depth at different positions in your profile, which is very handy and which gives you a lot of data and a lot of accurate data, which you can use in our Q Commander software and then use it in the RQ instrument. What the problem often is, you usually don't apply the ADCP boat when you have the maximum water level. So usually you apply it when there is fairly good weather at medium water levels. So let's say we would do the mapping with ADCP at this water level here, and then you get the information for the cross-sectional area for this part here marked in red. But then you have situations where you have higher water levels. So it's the green sections here on the left and at the right side of your river. And you don't cover this area with an ADCP boat. So you have to add this area here to your cross-sectional profile as well, and add it to the discharge table, so you can determine the discharge at very high water levels as well. But then how are you going to do this? Let's say we took the river's edge where we put in the ADCP boat as our first or initial reference called RE. And then we say, okay, our water level goes much higher, And so we define a new reference point with the methods we have mentioned before. So a safe, a concrete, a stable reference point somewhere on the river edge or on a bridge or somewhere. And we measure the offsets, the vertical offset and the horizontal offset between these two reference points. So we can shift all the data we have gained here with the ADCP boat, we can shift them to this reference point. And you can do this by the following procedure. So you survey the area of the dry section as we did before. So you go there and you measure from our new reference point the horizontal distances to the river, and you measure the depths at these points of the dry area up to the point where you have used your ADCP boat. And also on the other side of the river, you measure the horizontal area and you record the vertical distances from the dry area as well. So and then you add an offset to the depth and distance of the ADCP data. Then you add the points of the dry areas, and finally you can import this information in the Commander. And the procedure is very handy with the ADCP data because you can get this information as a CSV file that you can import in Excel, and this file would look something similar like this one. You have some general information about the profile, you have the time when you took the ADCP data, and you have the depth measurement and the horizontal distance of your measurements relative to your initial reference point. So then you're going to add the offset from the old reference point to the new one. I'll go back again. So we want to add the offset from RA to RB in our Excel sheet. So we add two new columns. We can call it the same or differently. Then you specify the offset. So we say our additional depth offset is 2 meters, and in the horizontal distance, the offset is 5 meters. So again, if you go back to our profile, so the vertical offset we have specified in this example is 2 meters, and the horizontal offset would be 5 meters. And we're going just to add this information to the original data. So for the original 0.73 meters, we add 2 meters and get 2.73 meters. And for the horizontal distance of 0.01 meters, we add 5 meters and get 5.01 meters. And we do this for all the points of our ADCP measurement. And the next step is, as we said, we want to add dry area on the left side and on the right side of the river. So in our Excel sheet where we have adjusted the offsets here, we add some extra lines for the left shore and some extra lines for the right shore of our river. And then we can add our depth and distance measurements here as well. So in our example, we have 2 more additional points on the left side at a distance of 1 meters, a depth of 1.5 meters, and at 3 meters depth or vertical distance of 2.2 meters. And also at the other end of the cross-sectional profile, 2 additional points. And then we can go into the Q Commander and import the CSV file and get the cross-sectional profile of the whole river or channel with the ADCP data down here and the manually added sections of the left and right side on each side of the river here. Okay, when you have all these data imported, you have to make sure again that your active levels are not more than 16, because you can just import 16 level lines into the Q commando. So you probably need to deactivate different lines or add other lines, so you reach a count of 16. And then your discharge table is actually ready, or you have to adjust the K factors or roughnesses. And when you're done with that, you're ready to upload your discharge table to the instrument, to the RQ command, to the RQ sensor. Okay, finally, I want to address one more thing. You might have the situation where you have a river or a channel with an installed gouge plate with a certain zero level. So, for example, you have a simple channel with a bridge over it, and beside the bridge you have a gouge plate with a zero level of 1 meter below the lowest point of your cross-sectional profile. And say then you want to install an RQ instrument onto the bridge, and you want to gain automatic water level and discharge measurements, but we want to make sure that our automatic measurements match the gouge plate that is already installed. So again, you need to determine the offset between the lowest water level or the bottom of your channel or river and the 0 point of your gouge plate. So in our case, we have an offset of 1 meter here, and we use this one to correct or to input our cross-sectional data into the Q Commander software. So you do the cross-sectional survey as you did before, or as we have discussed before. You record this information in an Excel file, and then you import these data into the Q Commander software. So we again get the cross-sectional profile in our Q Commander software as we did before, and as before, we see on the left side the water level is negative, with -7 meters is the bottom point of our cross-sectional profile. And we have said that our 0 point of the gouge plate is 1 meter below our deepest water. So what we're going to do is just go into the settings again and adjust our 0 point. And in our case, we say our 0 point is 1 meter below the lowest point. And we just add this additional meter to our 0 point, in our case 8 meters. And then we get a water level scale in the right dimension that matches the gouge plate that is already installed. So 0 meters is 1 meter below the river surface, and 1 meter is at the lowest point here. So these two scale match now, just by adding the correct offset in our 0 point definition here. And also we can do as a check the calculation of the discharge. So if we say we have a water level now of 1 meter, then we still don't have water in our channel, so the discharge must be 0. So if we put that into the discharge equation, and we multiply velocity times K factors times cross-sectional area, which in this case is 0, then our discharge is of course 0. Okay, and after you're done with the cross-sectional profile, you have recorded all the data, you have imported it into the Q Commander software, you have built the discharge table with the correct K factors and the correct roughness. Then you might need to make sure that you upload your discharge table to the sensor. Otherwise, you may get errorless data or no data at all. So go into the command section of the Q Commander and press upload discharge table or say adopt discharge table. The difference is only if you say upload discharge table, then the discharge table is directly sent to the RQ and written to the firmware of the RQ instrument. And if you say adopt the discharge table, then the discharge table is just transferred to the setup file, which is still on the Q Commander software, and it's still not on the instrument, but you can see it in the setup of the instrument. Yeah, this is or is often a case that has been forgotten. So a lot of work was done and to record the cross-section profile, and people just missed to upload the discharge table to the sender. But this is just an easy part, and just make sure after you have uploaded the discharge table, check your data and is it correct, and then you're fine with your complete setup. Okay, so far an introduction to the cross-sectional surveying and the way you build the cross-sections in the Q Commander, how you use the Q Commander to build the cross-sectional profile, which functions are available, and what you have to pay attention to. This is covered in our next lesson, which takes place tomorrow, and then you will get the complete picture from surveying to building your cross-sectional profile for your discharge measurement. So thank you for now, and if you have now questions regarding the cross-sectional surveying or cross-section mapping, then you're welcome to post your questions now, and we will be happy to answer them for you. And as mentioned, if you have questions about the Q Commander software itself, how to program your cross-sectional profile, this is covered in tomorrow's lecture. Okay, thank you.
Thank you very much, Johannes. Great lesson. So now we have seen how we can actually, or how we have to take the measurements, how do we have to work in the field, and how do we have to think in the field to get to the cross sections. And as Johannes said, now the Q&A session is open. Now is the time to ask your questions. Please feel free to do so. I have here already a couple of first questions. One of the first ones is, which is the most used input type and which are the easiest one to work with? So Johannes?
Yeah, we have seen in the introduction of our webinar that we have 3 different input types, which are called height input, sea level, and distance to ground. And the most type that is used the method that is used most often is the distance to ground, because it's very easy to apply, because you're usually standing above the water and you look downwards to the water surface, and you can measure from your bridge downwards to the water level, and that is mostly the easiest way to do your cross-sectional profile. Just make sure that after that you adjust your 0 point correctly so that you read positive values.
Okay, and which one is the easiest one to input?
The easiest one to input would be the height input, because there is no conflict in positive or negative values. Then you just say the bottom of your river is the 0 point, and you measure from the lowest point upwards the river's edge, and then you get positive values, and you don't have to bother about any positive or minus or negative values.
Okay. Is there a big difference between height input and sea level input?
These two inputs are essentially the same, except that you use your sea level datum as a reference in the sea level input, and in the other you use the lowest point of your profile as an input, and that is the height input. So the difference is only the offset between the sea level and the lowest point in your cross-section profile.
Okay. And one of the most asked questions, how do I have to calculate, or how can I, or how do I have to calculate the K factors?
Well, manually it's defined as the ratio of the mean velocity of the river to the local velocity. But in the QCommander software, the calculation is done automatically by specifying our 16 water levels at the positions that are most suitable. And with that, the QCommander calculates the K value automatically.
So if I summarize that, basically, we just have to input the cross section and the software is calculating everything by itself.
Yes, essentially, yeah.
How do I measure the radar position correctly? Can I measure it from everywhere, or do I have to follow special rules for defining the radar position?
This is sometimes quite easy. Sometimes it can be tricky depending on the river you're having. If you have a straight river which is relatively deep and large, then you can see visually that the highest velocity is about roughly in the middle of the river, and that would be the position to place. If you're not so sure where to place it, you can use other methods and determine the position of the highest velocities. And you could use an RP instrument, for example, or other methods to determine the position of the highest flow velocity. But again, it's not that accurate or it's not that critical where you put your instrument, as long as it's not too close as long as it's roughly in the middle of the river, highest velocities.
Okay. Are there any questions left from the audience? Please raise your hands or post the questions inside the chat so we can cover and answer them as good as possible.
Mm-hmm.
How about another question, Johannes? How about the reference points, the vertical and the horizontal reference points? Do they have to be close by the cross section, or can they be a bit far off, or how best to handle the reference points and how to document them?
Mm-hmm. Well, most importantly is that you have fixed reference point that you can remember and that you can take as a 0 point repeatedly. So if you go there on your site 1 year later and you still can identify which point you have used 1 year ago, then it's a good reference point. Regarding the vertical and horizontal reference point, they actually don't need to be the same. So it might be good to have a vertical reference point on a bridge where you have a defined road surface, and you can take the end of the bridge or the end of the hand railing as your horizontal reference point. So they actually don't need to be the same, they just need to be clearly be identified individually.
Okay.
Yeah.
Okay.
And, yeah. Okay.
No, please.
They don't need to be right close to the river, so they can be a couple of meters off. And it's better to have one of these points than just to have a point in the sand that might get eroded over time. So choose a point that is fixed and maybe further off from the river's edge.
Okay. Okay. So there are no questions anymore. In this case, we would close the session for today. Thank you for participating and thank you for your attention. We are happy that you're here. We are looking forward to the seminar tomorrow. The seminar tomorrow, the lesson tomorrow is building up on this section or lesson today. Today we covered how we actually can measure and survey a cross-section in the field. Tomorrow we use this knowledge to set up the measurement files, and from the measurement files we transfer the information into QCommander, into the software, and up into the measurement device. We take a look on all possible ways of doing that. So please stay with us, and we are happy if you join us tomorrow as well. And have a nice afternoon, have a nice evening. Thank you for participating, and have a nice evening. Bye.
Bye-bye, and thank you from my side as well. Yeah. Have a good day.